Okay, welcome to the next episode in the J Team Technology series. In this episode, we're going to cover imaging sciences, specifically MRI. Now, this is a science that was developed in the 70s, um, utilizing sciences that existed for some time. And actually, the history dates back to the creation of the X-rays back in the 1800s by William Conrad Röntgen, who stumbled upon imaging uh, by chance, actually. But we're going to get into how this 3D imaging that is magnetic resonance imaging has come to be very beneficial in healthcare and some of the pros, mainly just pros behind it. So we're going to jump right in here. So what is it? MRI is cross-sectional imaging that allows you to visualize different densities and tissues in the body in three-dimensional planes from various aspects. To a very thin slice proportion that allows you to diagnose very minuscule disorders and diseases. So, as you see here, basic principles that we're looking at when we look at MRI are pulse sequences, TR, which is known as recovery time, TE, which is known as echo time, and gradients, which are moving magnetic planes within that field. A magnet is comprised of an electromagnet, or MRI unit, is comprised of a very powerful magnet and an electrical field and a radio frequency current that is generated through this field. And all these occur in various planes. As a magnet has poles, as north and south, if you ever had a handheld magnet, you know that there's a positive end, there's a negative end. If you take two magnets and put them together, you put a negative and a positive, they'll attract. Two positives will repel. Every magnet has that kind of a pole. And that pole, you can imagine it like a straight line. Then you have what's perpendicular to that line. When you generate a current that's perpendicular to that line, and you do so in a helical manner, that is what generates a powerful electromagnetic field. So, as these images are formed using radio frequencies, it generates various forms of images. You can look at soft tissue, you can look at hard tissue, you can look at pathology, bone, muscles, sinews, nervous tissue, things you can't visualize in other imaging. And as you see here in this breakdown, the essence of it is it was invented in the 70s by Paul Lautenbohr and a few associates. It uses electromagnetism and radio frequencies that resonate from their interaction with hydrogen protons in living matter. That's why the myth that you hear about, can you image a mummy? It would be no, because there have to be active hydrogen protons in the matter. Now, the amount of time it takes for tissue to recover back to its resting state. You have a magnet with this hydrogen protons. Those protons are excited with an RF pulse, a radio frequency pulse. After that excitation pulse, they return back to their original state. That's the recovery time. And however long that period is dictates the type of tissue that it is. So, each pulse starts the process, and the time between these is a TR. The time from the start of the pulse to the time of the echo of that tissue, that's the echo time. And I always imagine it like the consistency of matter and almost like catching up to something. What's gonna bounce back to you more readily? Throwing a ball off of water or throwing a ball off of a wall? You're going to say, oh, it's going to bounce more readily back off a wall, right? Exactly. That will be a shorter echo time. And it's the same way in MRI. The echo time is shorter for denser matter. or what we would call T1 imaging, T1 relaxation. T2, or more fluid matter, such as blood, CSF, or other or pathology, that's going to be like water. It's going to have a longer echo time to it. These are the essential structures of MRI. T1 weighted matter has a short recovery time, short TR, short TE. T2 weighted matter has a long recovery time, TR and TE. And all sequences work around these principles. And then you have varying angles at which these hydrogen protons are precessionally spun. It could be 90 degrees, it could be 180 degrees, and this also affects the contrast of the imaging that you achieve. Now, the gradients I mentioned are little small, you could almost call them like mini magnets that are introduced into the field that allow the field to be strengthened and weighted differently. So they'll have a flip angle, which is that angle of that excitation pulse again. It'll be less than the standard 90 degrees. That standard perpendicular line that I mentioned, they will be less than that, creating a different precessional frequency with those protons and resulting in different imaging. They also interact with the different planes I mentioned. You have the long plane of the body of the magnet, then you have that perpendicular plane, and then you have that cross-sectional plane. So there are three planes. VO, or the body's longitudinal plane, the Y, and the X plane. So then you have intermediate imaging, where you have the meshing of two worlds. Longer TR, shorter TE, or vice versa. This creates little nuances where you can visualize anatomy in different ways. A lot of times it's used for bone imaging. Here's a graph breaking down how it would look visually. You see that angle there, and then you see that excitation pulse, and then you see this long period of time before it gets back to that 90-degree state, that recovery time. This is the TE and TR visually displayed. And the flip angles, once again, you see down here, flip angle of 28. TR and TE, not necessarily relevant in those cases when you're utilizing the gradients, because you're interacting with the magnetic field in a different way. And we'll get into more depth in this in the future, but these are the core principles that everything revolves around. Two different images here. You see one is a gradient type image. One is a fluid attenuated image that's T1 weighted. You see that there's a lot of dark contours to this. So this has inversion, which is another factor. Inversion time, where images can be inverted. There'll be an inversion pulse along that same line that gives you the excitation, that inverts the magnetization. It gives you an image that's actually like a contrast that's used to attenuate fluid or fat, which is useful for pathology as well. And then the image itself is actually created in a pixelated format on a grid. And just like with a television, you have pixel size that determines your resolution. You can adjust this. Encoding the image to this takes time, so you can adjust how that's encoded to shorten your scan time. And in that process, you'll have reformatting such as this. Here you have angiography, a restructured image. You reformat the slices and you create what's known as a maximum intensity projection, which highlights the vessels as you can see here. Very handy stuff. And so this kind of breaks it down that, at the end of the day, everyone wants to arrive at a diagnosis, right? And that's why recognizing pathology is what it all comes down to. You'll find varying protocols at different facilities. Regardless of what you find, it all comes down to understanding what's being looked for, pathology and quality imaging in order to find concurrent things that they may not be looking for. When you learn how to get your imaging and how the science works, you can manipulate anything you need to get what you desire imaging wise. Because you're also going to deal with these artifacts. Artifacts occur when there's some type of an infiltration of radio frequency into the field, some kind of an obstruction, or maybe an oversaturation of fluid. A big artifact actually is one where there's too much fluid in the liver, and it actually completely skewers abdominal imaging and creates very severe artifacts that can actually mimic pathology. Being aware of these is also key to being an effective technologist. Don't panic when this happens. You can adjust parameters such as the echo time, because echo time is what creates a lot of the artifact, because that's what's creating your imaging. You're bouncing that echo off of material. So if you're getting a lot of artifact, manipulating that echo time or even your bandwidth can go a long way to reducing it. So we won't get into this too much now, but different softwares have different methods of reformatting their imaging in order to look at blood, in order to look at different values or different weighting of different material and propensity in the such as brain imaging, perfusions, diffusions. A lot of that is software heavy. The principle is just that you're separating and contrasting portions of an image in order to get and extrapolate a certain material, matter, or pathology. And it's just using the software to do that. So this is what gets into more of that here, subtractions. When you take two images, you remove the anatomy to show only pathology by overlaying the images. There's a lot of different artifacts you run into. If your field of view isn't big enough, you can have wrap artifact. You can have zipper artifact from, as I mentioned earlier, RF infiltration. This is an example of aliasing or wrap artifact. Increase your field of view. You can switch your phase and frequency direction because you have your frequency and your phase direction with your imaging. Frequency is going along with the excitation of the magnet, and that phase is what's going to be going parallel. And a lot of times your artifacts occur in that perpendicular, I should say, phase direction. You have Gibbs truncation artifact, which can be remedied with fat suppression. So many things you can do. There goes an example of the zipper artifact I mentioned. Make sure that there's no leakage into the room, the door isn't open, etc. These are things you learn over time. So we'll get into more of this later on. But this was just to whet your appetite. And this will be the beginning of a series where we will discuss the magnetic resonance imaging sciences, and we may even get into some other radiological sciences time permits. But this was to introduce you to it and also let you know there will be interactive classes and podcasts in the future upon request. to discuss more in depth the sciences of MRI, to prepare you to take your exam, to work effectively and confidently in the field, and bridge and cross train into that modality if you'd like to. The full curriculum is actually here. So that can be done on a one-on-one basis, as well as some of the software I've created for to allow you to practice these things in real time. Those will all be released through my site and through direct contact. So this was just an introduction, and perhaps we'll get into more depth in the future. So that'll be it for that. Take care.